In this question, 1b, 4b, we're asked to calculate the most probable speed, the mean speed, and the mean relative speed of hydrogen molecules, that's H2, in air at 20 degrees Celsius. So a more straightforward kind of question here would be just to calculate any one of the benchmark, any one or more of the benchmark speeds for just a pure gas. But this is H2 in air. So, in which one of these does air actually become a factor? Well, the most probable speed, the one we're looking at right here, the formula for the most probable is 2RT over capital M. So capital M is your molar mass. And here the unit should be kilograms per mole. So let's just look at the most probable. So I've got hydrogen gas in air, 20 degrees Celsius. My temperature, again, it's 20 degrees plus 273.15. So I can put it into my solution like this, or I can do this here, establish it has 3 significant figures on it, and then put that into my expression. But everything is done in one big lineup. So I have my value for R is 8.3145 joule per k mole, but a joule is, okay, so right here, this is my conversion. So I'm saying that a joule is a kilogram meter squared per second squared. Okay, so I'm canceling my joules, and I've got my temperature, 293 Kelvin. And on the bottom, I have my molar mass, and my molar mass is, remember, it's H2. And this is 10 to the minus 3 because I have to have it in kilograms per mole. So joules and joules, they cancel. Kelvin cancels with Kelvin. This kilograms on top cancels with this kilograms, the top part of this unit. And what's left? The moles went out. So I just have meters squared over seconds squared. And that's fine because that's still within my square root bracket. So my answer, and this is in the calculator, but I put it down here because this is my copy that I used to grade. So I actually wrote that down so that I could recognize it on your paper. But normally that's still in the calculator. Meters squared per second squared, then the square root of everything, and now I've got the units that I want, meters per second. So it's very, very clear how all the units cancel, and that's what you're aiming for. And again, trimming it back to 3 significant figures. So you could either write it as 1550, because the 0 is not significant, meters per second, or 1.55 times 10 to the 3 meters per second, which is right down here. So that's the most probable. The mean speed is 8RT over pi m. So again, same idea. You're using the 8.3145 joule per k mole, temperature in Kelvin. This is kilograms per mole. Pi doesn't have any units. It all works out the same way. And now I've got 1750. And for the mean relative, that's where the idea of this being in air becomes important or relevant. Let's just fit this on here so I can see everything. I'm not sure I can. Okay, so you see it's the relative, right? So if when you look in the textbook and you're looking at the relative speed, you might see the one where it's the mean speed multiplied by root 2. So that looks like a great one to use because they've just asked us for the mean speed. So be careful. The mean relative speed is how fast the particle is going compared to the next guy, nearest neighbor. And when it and its neighbor are the same, which is the case for a pure gas, if we were just asked for H2 in H2, then that would be fine. because we're asked for H2 as a component of air, then my mean relative speed has to be this formula here, 8RT over pi mu. And the mu is the reduced mass. And the reduced mass takes into account that A and B particles are not the same. But I still want to have one value for a mass. And the reduced mass is, if you just look down here for a second where I've substituted it in, it is if there are two particles, A and B, or two different kinds of gases, and here is H2 and air. So I looked up in the textbook a molar mass for air. I know that sounds funny, but it's an average of weighted average of its components. So I have 0.029 kilograms per mole times the other one. So it's the MA times MB over MA plus MB. So I have molar mass units, kilograms per mole times kilograms per mole divided by kilograms per mole. See, because I'm adding them in the brackets as numbers, and the unit is outside. So those units cancel, and I'm left with just units of kilograms per mole for my reduced mass. Everything else here is straightforward. I have my 8, my R value, which is joule per k mole, but a joule is a kilogram meter squared per second squared. So I want to get rid of this joule, and I put it in. It's kind of like 1 joule is a kilogram meter squared per second squared. That's a conversion factor for my units. And the temperature, don't forget your square root, and so on and so forth. Then I get an answer of about 1810 meters per second. So the main thing to point out here was this reduced mass, and I'm using this one and not the square root of 2 times the mean speed because I have 2 different kinds of gases. Okay? So if you had another question where it was just, how fast are the particles of nitrogen going in nitrogen gas, then you could calculate, well, the most probable is this, the mean is this, and the mean relative speed, one nitrogen to another, is simply the square root of 2 multiplied by the mean speed. But in this case, I use a reduced mass. Once again, you'll see formulas for this that use Boltzmann constant K instead of the gas constant R. And in that case, they are the same, except for if K is being used here and small m is being used here. Remember, my R is a scaling, kind of a scaling factor that brings me up from the Boltzmann constant. Okay, so in this case, for example, it would be another formula would be 8kT, where K is the Boltzmann constant, over pi small m. So instead of kilograms per mole, it would just be kilogram, and that would be kilogram per particle, essentially. Yeah, so I know it's a very small number. Okay, but it's balanced by Boltzmann constant K here. So that's that.